Hello and welcome to Section 2, Backpropagation and Theano for the Rescue. In the previous section, we saw how powerful deep neural networks can be. We even trained a 5-layer neural network. But now, we might be asking ourselves, how can neural networks learn everything that they have to do, given only input-output pairs? To answer that, we have to understand how the backpropagation algorithm works. In this section, we are going to do first an introduction to backpropagation. Then, we are going to take a look at Theano, one of the most popular Python libraries in deep learning. And finally, we are going to optimize a simple Theano model. Let's start with our introduction to backpropagation. In this video, we will look how neural networks are trained and present a neural network class Scaffold with Python. Let's start defining a 3-layer network here, where x0 is the input data. Imagine the image pixels that we saw in the previous example, and the output of each layer goes into the next layer as the new input, till we get our final output y. This function f, g, and h of each layer is the layer nonlinearity. Do you remember the value that we used in the code? So yes, exactly. These parameters w and b are the layer weights and bias. In order to train a network, we have to define an error or a cost function between its output and a desired signal d that the network was supposed to return. Here, we are defining the cost function as the mean squared error. There are other functions like the categorical cross entropy that we used in the code, but this won't change the understanding of the general idea. In other words, this cost function just captures how well the network is doing so far. To train a neural network, we change its weights in the contrary direction of the gradient of the cost function. So here's the idea. The gradient points in the direction that maximally changes in an increasing way a function. Thus, a small change in the weights will bring some desired changes in the output. Now, let us pay attention to the terms of the gradient of L, the cost function, with respect to W3 and W2. Notice how part of the gradient of the upper layer, Wt, appears here in the gradient for W2. See the comparison? So yeah, this is why we say that the upper layer backpropagates error gradients down the architecture. The same thing will happen between W2 and W1. So here in the bottom, we have the general equation of the backpropagated error between two layers. Here's the equation. Now, let us check out a skeleton layer for a neural network class written in Python. There are 3 main methods to be defined. The forward propagation method that basically computes the output of a given layer, which for our case, using the equations in the previous slide, is the inner product between weights plus an input bias followed by the nonlinearity. That can be a hyperbolic tangent back in multi-layer perceptrons from the 80s, or ReLUs like we use in our code. All these operations could be implemented in NumPy, for instance. There is the backpropagation method that gets the input and the gradients coming from the layer above. This implements the general equation that we mentioned in the bottom of the previous slide. And here, finally, we have the update method that uses the gradients to adapt the layer weights and bias. See how we are using the gradients that we calculated through backpropagation to do the adaptation. Those are exactly the equations that we mentioned before. This learning rate here is usually a small constant between 0 and 1. Usually 0.01 or 0.001. It's usually a really small number. So yeah, In this video, we introduced the backpropagation algorithm and saw how it may look like in a pure Python implementation. In the next video, things will get really cool because we will take a closer look into Theano, which is one of the most popular ways of doing deep learning with Python, and is also much faster than our pure Python implementation, and it can compile to run on GPUs.